To our third day of our meeting. Before we get started, I would like to remind you that if you haven't registered your presence into this meeting, please scan the QR code in the table in the entrance of the room. Okay? Thank you. So to start our meeting today, I would like to invite you to stage the director of the STLO laboratory, Dr. Yves Leroy.
Thank you very much. Before I start, I would like to warmly thank Vasco and the organizers. Special thanks to Flavia, who did a wonderful work to organize this session and this symposium. And thanks also to the veterinary school who hosts this meeting. And before we start, I would like to tell you a funny story. I will tell it in Portuguese. This will be the only words in Portuguese I will give in this talk. Parece uma piada, mas não é piada, é uma anedota verdadeira. E você vai entender porque eu decidi aprender o português, por causa do Vasco. A primeira vez que o Felipe foi aqui no Brasil, foi com ele num congresso da Sociedade Brasileira de Microbiologia. Para nós, o português é um pouco difícil para dizer thank you, merci em francês. Você tem que dizer obrigado, obrigada. Nesta altura, nunca sabe como dizer obrigado, obrigada, confusão. O Vasco explicou, tudo claro, tá bom. Mas depois você encontra alguém prazer, tudo bem, como vai? O que é isso? O Felipe pediu ao Vasco, será que tem uma diferença também entre mulheres e homens para dizer como se dá um jogo? O Vasco disse, sim, vou te explicar. Ok, o Vasco explicou. Alguns minutos depois, o Felipe encontrou novos professores, novos colegas do congresso. Ele começou, ok, professor, prazer, tudo bem? A mulher, professora, gostosa, tudo bem? O Vasco. Então, o Felipe me contou isso. Eu disse que eu vou aprender o português. Okay, let's come back to something a bit more serious. I will present you my lab, and I will start with some tourism first, to make you feel like coming and visit us in Brittany, in France, and especially in Rennes. So my lab is here in Bretagne. This is the west of France, and this is a beautiful town with modern architecture and some Middle Ages areas, streets. And we're quite close to the Mont Saint-Michel. So this is not the castle of Versailles, but this is the Mont Saint-Michel. And we are also quite close to Paris by the high-speed train, TGV. It's 1 hour, 25 minutes. Sharp. Philippe told you it's only, Jouy-en-Josas is only 12 kilometers. But with the traffic jam, it's 2 hours. So actually, we're closer from the Eiffel Tower than he is. And of course, we have to see close to Rennes, and it's a bit further from Paris. So that's all the tourism. So the context. My lab is science and technology of milk and egg. And this is not pura casa. We are located in Brittany, as I told you, somewhere here. And you see that the west of France, a bit like Minas Gerais, is the state of milk here in Brazil. The west of France is the region of milk production in France and even in Europe. This is a huge production of milk and milk products in Europe. So here you have Normandy with Camembert. Brittany, we produce a lot of Emmental cheese. We produce a lot of butter and a lot of milk powder, especially milk powder. And we export this all around the world, in China, Australia, everywhere. And here you have what we call the creations, the traditional creations. And these are the countries or the regions of the very traditional cheeses. In Brittany, especially in Brittany, we are a more industrial production. So of course, while you produce milk, you transform milk. So we have many employees related to the dairy sector. So it's a heavy sector in this region and in France and even in Europe. So that's why we're located there. So milk production in Brittany is a few thousand producers. Brittany produces almost 23% of the whole milk collected in France. And we also have a lot of processing milk, processing plants. So some are very big plants, and some other are smaller. But we produce, as I told you, we mostly produce butter, milk powder, and Swiss-Bact cheese, Emmental cheese. As I told you, my lab is interested in the transformation of milk, not the production. This is something else. We just have a few research lines with production. We are mainly focused on transformation on milk and egg products. And you see that it is not by chance too. because we also produce in the west of France a lot of eggs. And we also transform these eggs into white egg yolk and stuff like that. So once again, it's a lot of employees. It's a heavy sector again in the west of France. So my lab is located there. We are around 130, 140 persons. Among them, we are more than 80 clinical staff, and we host regularly more or less 25 PhD students of the master students. And something a bit special in the research landscape in France, we host also research and development sector of private company within the lab. So about 10%, a bit more than 10% of our staff belongs to private company. They pay to be there, so it's a source of money for us. We build projects together, and this is a good opportunity to have some employment for our PhD students, and it's a win-win exchange. Okay. So research, we have 4 main lines of research. We try to increase the knowledge on the molecular and supramolecular structure of milk and egg components. And for 5 to 6 years now, we open our research line to plant-based foods, more and more food from plant, vegetables, legumes. The idea is for this famous food transition, we try to replace some animal proteins by vegetable proteins. We try to understand also the interaction, the protein interaction, protein lipids interaction, protein minerals interaction, to get some expected technological and bioactivity functionalities. And we try also to understand the digestion of this whole with some model of the digestive tract. For the physical-chemical part, we don't have any fermenters like Schlein fermenters and stuff like that for the moment, but hopefully we'll get some one day. So we have the stomach and the intestine, first part of the intestine, for the enzymatic part and biomechanic part of digestion. So we also analyze the transfer during technological processes. We are quite strong in cheese processing and also egg product processing and food processing. We have a platform for that, I will tell you about that. And regarding microbiology, which is my background, we characterize interactions between bacteria and the environment as a whole. And by environment, we include in environment, we include, for example, food matrix, but also the host. So probiotics and product quality, food safety, and probiotic activity are included in this microbiology team. This team is headed by Eric Guédon, who is here today. He will talk about some of the work of the team this afternoon. So these are just a few main results we got. I will go through it very quickly. This is just to mention that we are interested in how lactic acid bacteria interfere or affect the cheese ripening, for example. We also have some we talked about this a bit yesterday. We also have some words on Propionibacterium from the Reishi, which is a good bacterium. They make the holes in the emmental cheese. This is their job. But they are also very robust, and they also have very interesting probiotic properties. So we have some research line with Propionibacterium and their anti-inflammatory properties. Sometimes we mix different disciplines, and we make some patents on spray drying of probiotics. This is a way to lyophilize, let's say, to get probiotics powder and with an energy cost which is much, much lower than lyophilization. We also work on Staphylococcus aureus, and I will present you something more scientific afterwards related to this research line. So we have a research line where we study the intracellular life of Staphylococcus aureus. When it is internalized, we've shown that Staph aureus is able to delay some phase of the cell cycle of the host cell, and then divide and develop. And this is due to the production of some phenol-soluble molecules and some lipoproteins. And we also have, this is the only research line we have with the production sector. So we go up to the production, to the mammary gland of the cow, and we try to develop some probiotic strategy to avoid the use of antibiotic in vet medicine. So we are interested in Staphylococcus aureus mainly, and lactic acid bacteria to combat Staphylococcus aureus in the mosaic context. So we have some words on this, on selective lactic acid bacteria, but also on the microbiota and its composition as a whole. And we have something comparable to dysbiosis of the mammalian microbiota and stuff like that in relation to the mastitis, the sensitivity to mastitis, for example. So that's all. We organized in three main research teams, which are disciplinary teams, so microbiology, physical chemistry, and processes, and bioactivity and nutrition. And we have also two platforms. One is a collection of bacteria of food interest, a bit like a Severella, and the other one is a platform, a daily technology platform. I will tell you about that in the last two slides. And something like 5 years ago, 6 years ago now, when I took the head direction of this lab, we launched two transverse axes. So this doesn't mean that everybody has to work on this topic, but this was launched to help people working together, despite they work on completely different disciplines. But we have the same objects. And these objects, these axes are mission-oriented, and one of them is dedicated to optimization of infant formula. This is the milk powder for the babies. So we think that the gold standard is and remains the mother milk, the breast milk of the mother. So this is the gold standard. And the infant formula are quite good now, but it could be much better. And they do not mimic all the functionalities of the mother milk. So we try to fill in the gap. Okay? And the other one is more related to sustainability of our food system, and we work on mix between plant and animal food matrices. Try to replace some proteins, some animal proteins, by vegetable proteins, but to gain the same quality and the same nutritional value. So I will make a short focus on Eric's team, the microbiology team. So as I told you, we have a small research line on animal health. The objective is to reduce the use of antibiotics in pet medicine, thanks to probiotic or microbial approaches. A huge part of the team works on food quality, and the idea is to develop sustainable, safe, and good. Food is very important in France. Good fermented foods. We also have a research line, especially in egg products, because we cannot ferment egg. It's just impossible. Oh, it is possible, but it is pigs. So we have a research line on egg products, and then the idea is to reduce the safety risk due to salmonella, for example, and spoilage and waste due to some alteration by bacteria like the Bacillus cereus group. And also a food health topic where we include all the stuff on probiotics. So these are a few lines on the production. This is just to mention that Brazil, we co-author more than half of our paper with foreign teams, research teams, and Brazil is the first one. But we have two international associated laboratories. One is Bact with our Brazilian colleagues, and the other one is with China. And on the top three of our colleagues we publish with, you can find number one is Brazil and number three is China. Oh, this is an old one. Now China is on the third position. So we have, yes, we collaborate with many people. As I told you, two international associated laboratories with Brazil, UFMG, and with China Social University. It is something like 45 minutes by train in the west of Shanghai. And we coordinate also an international research network. We heard about this during the presentation of the author show in the opening session of this seminar. So one is dedicated to digestion, this is InfoGest, and the other one is dedicated to milk quality in general, from production to transformation. So we have also some platforms, as I told you. One of them is dedicated to milk technology, but also some other food stuff, but basically milk technology. We can reproduce at the industrial scale about 100% of what you can find in the dairy sector, in the industry. So heat treatment, filtration, spray drying, and of course, cheese making processes. So it's 800 meters square, and we have all kind of pilots and facilities to reproduce what we can find in the industry. So we can start with 1 milliliter of milk to 1,000 or several thousands of liters of milk, and see if what we have shown and demonstrated on 1 milliliter is still true for at the industrial scale, for the scale of the process, for example. We also have a huge collection of bacteria of food interest from dairy origin for historical reasons, but also and more from vegetal origin and some other origin. So that's all for the presentation of the lab. If you have any question or if you have a question, we can make a stop now. I will be happy to answer, or we can move to the next talk. Okay, we move. So, could you? So I will tell you about the characterization of Staphylococcus aureus strains from different host origin, and mainly those related to Mastitis in the dairy sector. So bovine, caprine, and ovine strains. And maybe 15 years ago, we started a job to characterize some Staph aureus strains that reproducibly induced severe or mild mastitis in ewes, in ovine, right? And we discovered some proteins that were really characteristic to some strains and not the other. And this is the point of this talk. This is also it's a good illustration also on how Staph aureus can be specialized in a given host and not some others. And this is also a good illustration of how research is a teamwork and even a network work. because we will travel from France to Brazil, of course, and to Japan. So we published this work a few years, maybe two years ago, in a scientific report, and we collaborate, of course, with Vasco's team, but also with Arvin's lab in the São Paulo state, and with the Japanese colleague, wonderful guy, who made a wonderful work on the characterization of the activity, the specificity of the activity of this new virulence factor that we discovered in Staph aureus. So I told you Staph aureus is a problem for the dairy sector at different levels, from upstream to downstream, all along the dairy sector. So it's a problem in terms of animal health. It is a major cause of mastitis and also a major cause of antibiotic consumption. So we have to combat, struggle against that. And it has a huge cost for the dairy sector, the dairy production. And when you go downstream, even at the end of the chain for the consumers, it is also a public health problem, because some of the strains that we find here can contaminate the dairy product at different stage of the milk processing. You can end up with some strains that produce enterotoxins within the dairy product, and then when you consume them, you feel sick, you vomit, and it's not a life-threatening infection, but it's quite annoying, and especially even more especially for the cheese producer. It's a very, very bad image. When you eat a cheese and you feel sick, you will not eat this cheese for a long time before you come back. So we have to fight against this, and of course, it is a cause of food safety and food poisoning. Staphylococcus food poisoning outbreaks in France are majorly based due to Staphylococcus aureus for the milk products. So Staph aureus causes huge economic loss for the dairy sector, so we try to combat it. So we made a lot of work on what differentiates the Staph aureus that we find in the hospital and in the farm and in different hosts within the farm. So you can see here that there are differences in the Staph aureus population. The primary host of Staphylococcus aureus are human beings. We all carry, probably all of us carry some Staph aureus here in our nose. Okay, it's a safe carriage, no problem. But sometimes it is an opportunistic pathogen, and sometimes it induces an infection. In animals, it's really the same. And there has been during the thousands of humankind history, there has been some host jump. One of the first was the host jump from human to bovine, ovine, and caprine during domestication of these animals at the level of the Neolithic. So it was something like 8,000 years ago. So this was demonstrated. And Staph aureus became adapted to this host. And you can see it at the genotype level. If you look at this tree, which is based on NRST, multi-locus sequence typing, this is the method to type the populations of some bacteria. You can see that we have some clutter complex that are very rich in bovine isolates, and some other hosts, like small ruminants, ovine and caprine, are very rich in some other clonal complexes. And you have here in this part of the tree, some human and other hosts like pigs or putti. Putti are also a very dedicated population of clonal complexes. So these are the different color corresponding to color complexes, and you see that for ears, for example, for ovine, there are 3 main clonal complexes which are very specialized to this host. So this is at the genotype level, the population level. At the strain level, And at the molecular level, you can find also some illustrations, some examples of host adaptation. And this is the work that we did a few years ago. We compared two bovine strains. One was associated with severe mastitis, and another one, and we will find, was isolated and reproducibly induced mild mastitis, but chronic mastitis in cows, in dairy cows. And in the core genome of Staphylococcus aureus, you've got one virulence factor which induces platelet coagulation. This factor is called the von Willebrand binding protein. The von Willebrand factor is something that we produce, the host produces, and this helps healing the wounds, okay? The wounds. So it coagulates the plasma, and then you go to the healing process of the wound. And Staphylococcus aureus is able to induce to coagulate the blood thanks to this factor, because they entrap these platelets and they provoke the coagulation. So all of them produce one copy of this gene in the core genome. But it appears that there is a second copy which is carried on a pathogenicity island, which is called the bovine variant of von Willebrand binding protein. And since it is on a mobile genetic element, it is present or absent depending on the strains. So it's quite easy to show. Here you have a rabbit plasma. This is the plasma that we use to mimic the human plasma. So you see that it coagulates the plasma. It's quite easy. You take the plasma, you put one droplet of Staph aureus supernatant, you wait for a while, and then you put the tube upside down, and you see that there is a platelet of plasma here, and nothing here for the bovine plasma and equine plasma. And in this strain, which is more adapted to this host, you can see that they have the same core, the same gene of von Willebrand binding protein on the core genome, like this one, but they have the second copy, the bovine variant, and they are able then to coagulate bovine and equine plasma. So this is one example. We've seen genotype population, but at the molecular level, you can see that Staph aureus has developed strategy to timely adapt to a host. So we wanted to discover what could be a marker for severe mastitis and mild mastitis, and for that, as I told you, it was more than something like 12, 30 years ago, and we published this in 2009, this method. Just the description of the method. We adapted something that was already used in cancer research. This is a serological proteome analysis. So for this method, you take one given strain of Staph aureus, in our case, and then you make an experimental infection. For us, it was an experimental mastitis in ewes, right? And after a few days, you collect the serum, the blood and the serum of the ewes. And in parallel, you make a proteome analysis of the same strain, the one that you used for the experimental infection. So you make a 2-PCR, and you make the Western blot, and transfer it on a membrane, and you make the Western blot with the serum that you have collected. And this will reveal the proteins that are indeed produced during the infection and that trigger an immune response in the host. So it's a good way to find some candidates and some differences in the strain behavior within the host. So doing so, we discovered that there were a kind of core serological proteome and some very specific proteins. And I will focus on these three. One of these three which were found associated to strains that make mild mastitis. So almost nice staphylococcus aureus. So the idea then was to try and find what were the roles of these proteins, or could they be some good candidates for vaccine or whatever. I will tell you about one of them. So we found this on two different strains, one which made severe mastitis and the other one mild mastitis, and I will focus on one which is associated to the strains in mild mastitis. So we can find it in the strains that we use for the infection, and we tested on 5 other strains isolated from mild mastitis, and you can see that you have on Western blot, you have a signal here, and nothing in the same region of the 2D gel, nothing for strains isolated from acute or severe mastitis. So we had a look at one of these proteins, and we discovered that it was highly similar to exfoliative toxins. Exfoliative toxins are a particular toxin produced by Staphylococcus species, not only Staph aureus. There are proteases, in fact. So it was quite identical. It was quite close to type D exfoliative toxin. So here is the 3D structure, and this starts our trouble around the world. So we send the DNA to our lab to produce the protein in the E. coli system, if I remember well. They crystallized it, and they made the structure of the fine structure of the protein. So we have this that we called, at that time, we called it an ETD-like protein, and compared it to ETA or ETD, which are two other types of exfoliative toxin. So the exfoliative toxin activity, as I told you, is a protease activity. It targets a very specific cleavage site on desmoglein 1, which is a protein involved in the tight junction, the junction in between the host cells in the tissue. So it disrupts this desmoglein 1, and then the epiderm becomes loosey, and the symptoms are just like if you were burnt with boiling water, okay, a burnt wound. So these are a few features of what you can find. This is especially found in young children. I don't know why, but this is especially found in young children. In humans, this causes the Staph aureus scalded skin syndrome. It's due to one single toxin of some Staph aureus strains, and it looks like something like this poor child has been burnt with boiling water. But this is also a problem in the farm industry, in the farm production, especially in pigs. Since some Staphylococcus eagles also produce this type of toxin, and they induce some epidermitis. Yeah. So we have to look at the phylogenetic of this toxin. So you can see that actually it's quite far from ETD. So we call it new ET. But at that time, we did not demonstrate its activity. So it's just like similarity comparison. So these are the exfoliative toxins that you can find in Staph aureus, Staph eagles, and the whole family is there on this tree. So this phylogenetic analysis was based on the amino sequence. At the genetic, on the genome level, we saw that, in fact, both strains, the one associated to severe mastitis and the one associated to mild mastitis, in ovine SOA strains, both carry the same ETE genes, except that in severe mastitis, in all the strains that we analyzed, the strains, EU strains, associated severe mastitis has a point mutation or few point mutation in the gene. And here it is functional. And in the bovine strain, you see that the vicinity of the genome is totally different. So here, we made a crystal structure, crystallography analysis in Arnis lab, and now we move to Japan. So I contacted Koji Nishifuji, and this is Mr. Exfoliative toxin in the world, and he was quite happy to analyze the activity of this new candidate. So it took the protein that was actually produced by Arnis lab, so it traveled to Japan, and Koji Nishifuji did some experiment with a PhD student of his. And he first demonstrated the activity, really, of this exfoliative toxin. It is a CD experiment. You just inject some of the toxin on the back of pups, mouse pups. And after 1 hour, you just caress the back of the pups, and with a single caress, you just push away the skin if the exfoliative toxin is active. This is the basic test to demonstrate the activity of exfoliative toxin. That's a bit cruel. So I did that, and you can see in histological analysis that here you have an epiderm 0.0 normal, and you can see here that the epiderm is totally disconnected from the derm. And he made some Western blot analysis, kind of Western blot analysis, immunological analysis, using antibodies that trigger, that target the external part of desmoglein 1, and used another antibody that targets the inner part of desmoglein 1. And you can see in the control at time 0 that you have something very clear here, and you lose totally the structure here. And this is really an enzyme and an activity that target this part of the protein, desmoglein 1, and the inner part is intact at time 0, and 1 hour after it is not degraded. So this was the first part of the demonstration. And then he used some tissue isolated from ovine or caprine, sorry, small remnants of epithelium from the tip canal. And in the control, this is the control, you can see that the epiderm is quite clear, good structure. And with ETE, our candidate, this was then a new time. We demonstrated the activity. It was different than all the other ones. So we call it type E exfoliative toxin. So ETE has an activity, and we lose, compared to that one, we lose the structure of the epiderm when analyzed through this immunological approach. So we did this with some other epiderm from other hosts, and we find that ETE degrades the ACE1 in ovine, caprine, and bovine. This is the control. You can see that with ETB, which cuts everything everywhere, you have a destruction of the epiderm, compared to that, for example. And with ETE, he found that, okay, there were some small remnants, but not on bovine, not on big remnants. So this is not specialized, right? So he did some more experiments, because he likes to work a lot with some other hosts, and demonstrated here you have the control, the desmoglein 1 intact, and it is, you can see that ETE digests desmoglein 1 in humans, in pigs, in mice, but not in dogs. So it's quite selective, in fact. So then we came back to France, and my colleague, Aurélie Nicolas, made some molecular modeling to try and understand on what is based this what is based on what is based this specificity. So she made a model. So you get different domains in the decimal plane 1, EC1, 2, 3, and 4. And the cleavage site is very precisely defined. It's here, almost in between EC3 and EC4. So when you have a look at this cleavage site in ovine, human, canine, and bovine, you see that the cleavage site is quite identical. So what she did is she modeled the decimal plane 1, and she used the model of ETE to try and find the most probable energy, the most probable position based on the energy of interaction or repulsion between the amino acids. It's not really my part, but she using the best out-of-document solution, she got very clear results. And we've got two orientations, in fact. One, which is called the on orientation, with ETE on ovine decimal plane 1. You can see that it is, let's say, this position, and it cuts. And the off orientation in decimal plane of bovine origin, it is another orientation. So the conclusion was that probably the docking step, the approach of the protease on its sites is probably the reason why it is so specific. So as a conclusion, for the moment, because we will have some new results probably regarding this with Harley's postdoc student, Jorge. Good. So for the moment, what you can say based on this work is that ETE is a new Staphylococcus virulence factor. It is quite frequently associated with ovine SOS isolates. It's a new example of host specialization, as I told you, of Staph aureus. It is found in Staph aureus strains also associated with mild mastitis in ears and not in strains isolated from severe mastitis. We don't know why. So it could be a marker for SOS virulence in a new mastitis context. And ETE, as I told you, provides a probably, we don't know why, provides a selective advantage for SOS colonization maybe and persistence in the udder at the surface of the udder. We don't know exactly why and how, but it is associated to that. Now I think of what Gabriel said yesterday. We have to be very careful about that. Correlation is not the cause or the effect, or it's not the reasons. So it's a correlation at that moment. So that's all. I want to thank all the people who were involved in this work. Inflam, team, STLO, especially Aurélie, Nicolas. The Japanese guys, wonderful work. And all the people from Vasco, from genomics lab and comparison, and from Alice lab, especially for the structure analysis. Thank you very much. ¿Preguntas?
About the interaction between the protein E and the receptor, you do some dynamics to see how.
Some dynamics, you mean?
Yes.
I don't know, to be frank. But the result, what I remember is that she was thinking of doing something more detailed, but it cost a lot of calculation time. So to get these results was already something quite long, in fact. But that's all. I couldn't say if she did something really dynamic.
But she performed some experiments like this. She tried to make the dynamics, but
I don't know.
why did it work?
Yes, Philippe.
Yes, I have a question. I would like to come back to your last comment concerning the correlation. So the demonstration you made is clear, and I just want to know if it's possible to get and look out mutants of start values, for example, yes, you do not do this, no? This is a
What?
because
If you consider that it is a selective advantage for colonization and persistence in you imagine the cost of the experiment that you have to put a GMO on a U, on several U's in a control condition, so it's not fluid.
At the same level, you can do this, but we want to answer the question, you need to perform the experiment of animals and
yes. You are not in Bact.
No.
So that's why. I could have done this. Nice.
Yes, you could do that in Mike with your Japanese.
Yes. But I forgot that you are obliged. So that's crazy.
For ethic reasons and money.
Okay, I understand.
Okay.
And so this protease is absolutely specific from this movement.
The protease.
Yes, this protease is a
Yeah, it's a protease.
It's absolutely specific from this movement.
As far as I know, these are the only proteases that target this cleavage site and this membrane one, this family of exfoliated toxins.
And it has homology with
Other
other,
exfoliated toxins.
but only no, but with other proteases.
No, the cleavage site, I think it's 7 proteases, if I remember well. We always find the same catalytic sites. But the rest probably explains the specificity why it cuts in some hosts and not in some others.
And it's in the outside, on the cell wall of the bacteria.
It's secreted.
Yeah.
That's why you can expand so much on the skin. The infection is not by Staph aureus itself. It's really the toxin.
It's regulated. The expression is regulated.
No. It's not probably it's under control of the AGR system, but it's a secreted protein. Usually, secreted virus factors are induced at the end of the exponential phase, and they are tightly controlled by the AGR system.
Could we imagine a treatment with one multi-protease, for example?
Okay, we're talking about that.
Okay.
They develop some peptide approach to try and inhibit it. Okay, we'll tell you about that, sure.
I also have a question.
Yeah.
Because, these proteases are really specific for certain isoforms. I mean, often, and humans. And I am a little bit intrigued about where this specificity comes from. I mean, because, they have this internal alpha helix. I will talk about that in a while. And this element is really characteristic of this concept. But I wonder if you, for example, you cut the alpha helix of ETA and you put the alpha helix of ETA instead. Do you think that will shift its specificity? Because we don't really understand that yet.
I don't know, but as long as we've not demonstrated that it indeed provides a selective advantage for colonization systems, maybe we cannot really answer. Probably the selective advantage of colonization is based on many other factors. Triggers, some of the parts, some of the domains on the surface of the whole cell. So there are also some other either instructor that we demonstrated is highly specific and host. Most of the time, I've got one example on the Portuguese train, and this is the lost part because it was useless in the Portuguese context. Okay, thank you.
Thank you very much, Dr. Evidua. For now, we'll have a 15-minute break, so you are all invited for a coffee break in the interest of your room. Thank you. We'll come back in 15 minutes.
Je vais leur demander.
About to start.
Sim, você.
Oi. Oi. Hi everyone, let's come back, please. We are about to start.
Você chamou para dentro, chamou para fora. Yeah, thank you very much.
Okay, let's start. Okay, before we start, I would like to remind you again to register your presence in today's meeting by scanning the QR code in the entrance of the room. Thank you. Thank you, Yvi. Okay, following on, we are pleased to have a postdoc from the São Paulo State University, Dr. Jorge Henrique Gonzalez.
I would like to thank the organizing committee for the invitation, especially Vasco and Flavia, and I would like to thank your presence too. So my presentation is kind of a continuation of what Dr. Yves have been talking about with explosive toxins, but I would like to bring the discussion more to a more structural, computational field, right? So, as you know, as you can see, I will be talking about computational strategies and the activities of the exploitative toxins, targeting orthosteric and allosteric sites. When I talk about orthosteric, I will be referring to the main active site, where the catalytic sites of the enzyme lie, right? And allosteric sites are all other secondary sites that you can also target to induce certain response. So, first of all, you can see here the structure of 3 of those exfoliative toxins that doctors have been presented to you in the previous presentation. A, B, and E. We talk about this one especially. And you can see that they are glutamyl canapeptidases. It means that they will cut the peptide bond after a glutamate residue. And they fold as they all have share a characteristic fold of certain proteases that they have also some special structural features that I will be talking about in a minute. As you already know, they are expressing certain staphylococcal strains, Staphylococcus aureus in this case, but there are other staphylococcal species that also produce these toxins, and my colleague Caroline will be talking about those other exfoliative toxins expressed in different staphylococcal species in a while, right after my presentation. These proteins are really, they are highly selective for skin proteins, mobilin 1, you already know about that. And they have some interesting structural features that are only present in these toxins. This N-terminal alpha helix that you see here, you won't find this element in other seroproteases. And it is also interesting that when you look at the active site and the crystal structures that have been deposited in PDB, you will find that this proline residue here, I don't know if you see here the oxygen atom, this residue, is pointed toward the catalytic serine residue, and it lies in the opposite direction in the other enzymes of the family. So to have an active site, you need this oxygen to adopt the opposite conformation, right? And many authors in the 90s, when these toxins were really started from a structural point of view, they said that the specificity that they were observing, I mean, the high specificity for this smoldering and the lack of activity against other broad spectrum substrates of seroprotease family, they attributed that characteristic to this flipped conformation of the residue position 192. But intriguingly, we observed other crystal structures. For example, one crystal structure, BTB, does have the residue position 192 in the correct position. So, and there is another crystal structure with this residue in the opposite position. So, it is a little bit intriguing if this motion will control the specificity of the enzyme. Why then we have both conformations in certain crystal structures. And in the end, I mean, there is clear evidence that these toxins form homogeneous in solution. We do not understand clearly if that will have any functional impact, but I will be talking about that in a minute. This image is recycled from its presentation, and I will not, I mean, you already saw this image, and it's the desmosome. I mean, it's a junction of epithelial cells, and you can see that these toxins, they cleave this mobilin 1, and then they destroy the connection between cells, and then they produce exfoliation by cleaving this mobilin 1. The mobilin 1 doesn't have a reported crystal structure, but other homolog proteins have been deposited in the PDB. They are collectively known as desmosomal coherence. And you see here it's mobilin 2, 3, desmocolin. I mean, they are all very similar, and they have sticky ends, and they bind each other in this region, ectodomin 1, and they, I mean, because of this interaction, they keep the cells together, right? And well, some authors have speculated that by cleaving the desmosomes, Staphylococcus will have some advantages when invading the hosts by escaping the nucleus, the immune system, and other advantages. And also some of these toxins, they have superantigen properties that can also be related to escape of the immune response. But I will not be talking about superantigen properties, but it's also an interesting feature of some exfoliative toxins. And here is, I mean, some images of bullous and patago and Staphylococcus aureus skin syndrome. Some of the skin diseases caused by the bacteria that carry the genes of these toxins. And here I would like to show you an updated model of this Moblin-1 because I already said that it doesn't have crystal structure. This one, differently from the one that it's presented, this one was obtained with AlphaFold, which is a paramount algorithm to generate models from the sequence right now. So you see here that it had 4 vector domains, and they bind here, in domain 1 from opposite chains, they will stick together to form the junction. There are calcium ions here also that are important for proper folding. And if you see, it was reported by Anakawa and co-workers in 2004 that this Moblin-1 will require calcium ions to properly fold. The presence of this ectodomain very far away from the cleavage site is also necessary. If you cut here across it and you create a truncated version of this Moblin-1, you won't see cleavage by the ETs. And then there is this motif here, QXXYTE, TOIE. Here, you see an alignment that is important for recognition. Because, the authors perform a sequence alignment of different, this Moblin-1, isoforms from different species. And what they observed is that in this region, ectodomain 3, there is this difference here in the amino acid composition. And then they performed some experiments because they knew, for example, that ETA, one of the exfoliative toxins that I presented in the previous slide, it doesn't take canning this Moblin-1. But then if you mutate the residues in this region of the canning isoform that are present in human isoform, then you observe cleavage. So they inferred from those experiments that this region must interact somehow with the protein. It must be a distant recognition site, right? So it will be the results that I will be showing here. Part of them are experimental, and other part of them are computational. I work with molecular dynamic simulation, which is a technique that models proteins as beads and bonded with springs. So it's a very simple model, if you will, but it does produce accurate results when you want to understand interactions with macromolecular systems and so on. So what we do is we have a force field, which is a bunch of equations of motion with different terms. I will not delve into these terms, but you should know that there are angles, bone lengths, dihedrals, and so on. And then we put these proteins, we embed the proteins into solvation boxes, and then we assign certain initial velocities to the atoms according to a Maxwell-Boltzmann distribution, and then we start a dynamic simulation and we see how the system evolves in time. And we can see binding, dissociation events, recognition events, and a lot of interesting properties of molecular systems. And also we have free energy calculation methods. We can derive energies for the interacting particles, and we can calculate free energies, which are associated with affinity. So we can know from this in silico experiments if two molecules will have a strong affinity or not, and we can assess the impact of a mutation or a chemical modification through these calculations. So particularly use one of these simple methods is molecular mechanics generalized form surface area, in which we model the binding event in vacuum without solvent. And then we simply add the influence of solvent, which is very important, by the way, by using continuum electrostatics, right? So it's a bunch of equations that will allow us to really understand how the systems interact and the affinity of the molecules. And then I will be, when you see this in common slides, I will be referring to this method. So that's it. And we also perform some umbrella sample and free energy calculations. This one perhaps is more intuitive, because if we have two molecules, we can pull them away and calculate the work that we need to separate the molecules. So we have an idea of affinity by doing so. And we slice it, for example, here, this is a reaction coordinate, which is simply, for example, a Cartesian axis. And we pull this molecule away from this one, and then we create different windows, and we restrain the protein to reside within a certain distance from the other, and we start simulating and collecting data. And from this data, we can retrieve the potential limit pools, which is the work that we're performing to separate the molecules, right? And of course, if this work is higher, is bigger, we can infer that the molecular system binds them tighter, right? And finally, there is also molecular docking, in which we, for example, we have two proteins and we would like to predict how they interact. So docking algorithms typically start searching for the conformational space and put the molecules in different orientations. And then there is another energy function that will assess an energy for each conformation. And then typically we end up analyzing those with better energies. And that's the way we predict molecular interactions using docking. Well, using those tools and some experimental results, we got to this results that I will show you. This is the crystal structure of ETE, ABAX, which was reported this year to the PDB. Right? This one is really interesting because we observed in the crystal structure two opposite conformations of proline 186, which is that one that I mentioned that probably is interfering with the catalytic activity. It is required to adopt this opposite conformation. So we observed both conformations in the same crystal structure with different occupancies. And what we observed when performing the umbrella sampling calculations were the trihedral that will put this oxygen into this position or into the opposite position. If you see here in blue, is that both states, this one and this one, they both have very similar energies. You have to look here to the middle. And then when we look at the transition points, because we start changing the angle and rotating this bond here, we see that through this pathway, we can reach the other conformation, the opposite conformation from A to I, right? Through this conformation particularly, by just adding to the system like 6 kilocalories per mole. It's not really much, so we can see that this calculation agrees with the experiment. And what we know is that this flipping equilibrium is something that happens all the time. So the protein is not really fixed into a particular conformation, and that cannot be the mechanism, the molecular mechanism that explains the high specificity of the toxins. Also, we perform some mutations here, and we put glycine instead of proline, because glycine is observed in other proteases that are really promiscuous and have high activity. And we wanted to see what happens with that. And we analyzed B8 protease, which is another stop protease, glutamate protease. And when we observed the PMF in this energy plot, we observed that the active conformation, the one oriented in this direction, is really more stable than the other one. And the same happens if we put glycine, which is the residue that we find B8 protease, as in the equivalent position. The same happens with ETE. I mean, an ETE with a glycine residue in this position would behave in terms of the orientation of the oxygen atom like a B8 protease. And we said, well, probably that will lead to an increase in activity increase if the activity actually depends on the position of this oxygen atom. But what we observed when we perform kinetic assays with this synthetic substrate is that both the mutant P G it behaves really similar to the wild-type protein. So this really shows that there is no influence of the flipping conformation into the activity of the protein. And then we analyzed the formation of oligomers by ETE by using cytosol exclusion chromatography and also SACs. And all these results show that it eluted as a dimer in solution. And the same was obtained for EXHC, another protein that my colleague Carolina will be talking about, is another exfoliative toxin expressed in Stoke, Missouri. It also elutes as a dimer in cytosolution chromatography. And so we had previous evidence also from other laboratories that this toxin also elutes as a dimer. So we were intrigued by this fact and we wanted to know whether this had an impact on the function of the protein. And interestingly, also, we obtained two crystal structures of ETE showing dimers in the asymmetric unit. But as you can see here, these two structures are different. So the protein is not crystallizing into specific conformation, even as if it is a dimer, which corroborated in cytosolution chromatography and SAC experiments and so on. We did not observe a single conformation in the crystal structures corresponding to those homodimers that we were observing in solution. So we performed several in silico analysis, and they all concluded that these two structures are not stable in solution, and therefore they must be crystallographic contacts. Then we performed all those calculations that I briefly showed before, involving docking and dissimulations and MGDSA and for sample calculations, and we ended up finding this structure as the most likely conformation of the homodimer solution, where we see the participation of a loop that we term loop L1 here. And as you can see here, this loop is really characteristic of the exfoliative toxins. When we compare this region with other certain proteases that do not form dimers in solution, we see that this loop is missing. And also, when we created a model of the probable interaction of the peptide linker, if I put on 3 and 4 on this moment one into the active site of ETE by modeling with trypsin in complex with another peptide that has a crystal structure reported in the PDB. We observe here that this peptide will adopt a conformation spanning across the active site of ETE. And if we superimpose this structure with the structure of the homodimer that was protected, we see that there is a clash here. So probably the enzyme will have to monomerize in order to fit a peptide that will span across its active site. So probably monomerization is required for that. And then I am working right now in the interaction of ETs with this moblin 1. What we know is that this ectodomin 3 interacts with the protein somehow because it has this motif that was determined through mutagenesis. And we know that these resins are important for recognition with ETA. So we perform the docking simulations in this HDOC server, and we added some restraints because we wanted this motif to interact with the protein, and we know that this region here must lie into the active site because this resin is cleaved. So by adding those trans hormone, we ended up with 2 possible conformations, and this conformation was ruled out because of free energy calculations are performed and that show that this model was not really stable. So we ended up with this one here. I will show some properties of this model. But first, we needed to add the other parts of the protein because this model is not just a domain; it's a multi-domain protein. So we added ectodomain 4 to that structure, and then what we see is the following. This is the confirmation of ectodomain 3 in conflict with ETA that we just found through molecular blocking and applied some constraints about those simulations. And we see here that in order to fit the linker between two ectodomains into the active site, this one here, ectodomain 4, will have to adopt a position that will clash with the protein. So some kind of motion is required for the protein to properly fit into the bioconformation. So by rotating this model, this ectodomain, we can reach this other solution here, where clashes are avoided, and then we perform long simulations to sample the most stable conformations, and we ended up with this model here, where we can see that there are no clashes. Ectodomain 3 is this one, and this one is ectodomain 4. And we see that there are certain key interactions in the active site between the resin that is cleaved, right? And some particular resins of the protein that confer specificity and are important for the activity of the protein. This has been reported already through mutagenesis experiments. This lysin 216 and this histamine residue. They are all important, and they are interacting by model with the glutamate residue that is cleaved. And then we see another important feature here, which is the interaction of the N-terminal alpha helix, which is characteristic of these proteins, with the region that contains the residues of the motif that was found to be important for the interaction of hemoglobin with ET. So I think that this model explains a lot of experimental data, but we are working intensively to get a crystal structure of the system. I mean, we're trying to do that, but we don't have crystal structure yet. So this also raises the possibility of designing molecules that will interact with the N-terminal alpha helix and will prevent interaction of this hemoglobin and exfoliative toxins. So it is a potential site for the allosteric site, because it's not within the active site, to design molecules that will interfere in the process. And also there are old reports about peptides that are also cleaved by exfoliative toxins. These two peptides, in my knowledge, melanocyte-stimulating hormones. They are cleaved after this glutamic residue by ETA and ETB. And I also predicted the models, the structural models, with interaction of those peptides with ETE and ETA. And you can see also that the glutamate residue is here, interacting with the characteristic residue of the active site, and you can see that they all adopt a very smooth information across the active site. And these interactions that are formed here are particularly important for the design of new molecules, because these peptides can inspire new molecules that will act as inhibitors of the interaction process of the ETs and the hemoglobins. But we cannot really use peptides directly as drug candidates because they are degraded by all the proteases, they are immunogenic. They have a lot of features that are not suitable for drugs, right? And then we know that there are strategies to deal with those issues, to increase the stability against proteolysis, to increase affinity for the protein target, increase permeability for membranes, intestinal absorption, and also to lower immunogenicity. And I mean, there are certain chemical strategies modifying the peptide backbone or introducing certain modifications. And we will be talking about cyclization, specifically through stapling. Stapling are chemical modifications that are introduced in certain positions of the peptides. And you see that we create these staples they rigidify the structure of the peptide, they lock the structure into suitable conformation to binding, and then they increase not only the stability of the peptide, but also the affinity for the target protein. They can be used in, I mean, you see here some examples of crystal structures of stable peptides into the active site of some important targets that were studied by these authors, Xu and co-workers. This is not related to our work, but it's just a picture that shows that stable peptides are really interesting to work with. And they can also, staples can also be introduced into alpha helical peptides to confer more stability and rigidity. And also there is this inversion of the configuration from L to D that is also interesting because proteases will not cleave D peptides. So it's a way to circumvent proteolysis and to confer molecular certain stability that they need to act as inhibitors. So by taking into account those strategies, we took the model of ETE in complex with a linker that we find between the domain 3 and 4 small in 1, and we can see that we can add staples here into these two positions, and then introduce this kind of staple here or here, and we can also introduce some modifications into the backbone. So there's a certain, we can also invert the configuration of the glutamate residue at P1. I mean, we can also mutate certain positions of the peptide that are found in other isomers of the globulin 1 from different species, and so on. So this, we thought about different kinds of modifications, and we ended up analyzing different staples and different D or L configurations in the peptides in different positions. I mean, I think you will not see here in detail, but I mean, X here indicates a position where these staples are introduced, and then we create a lot of peptide variants, and we analyze the affinity in silico for the targets in this table. So we ended up knowing which of these variants will interact better with ETE or ETA. And here you can see some models for best candidates that produce the best results in the previous analysis. So you can see here the peptides interacting with the active site, the glutamate residue into the S1 subsite of the protein, and you see the staples here that confer rigidity and stability to the peptides. They will no longer be very flexible, and they will be locked in a position that is suitable for interaction with the proteins. So we will be, our objective is to analyze the affinity of these peptides with the exfoliative toxins, which we hope will be coming soon. And these are the perspective for my work, is to not only, I mean, I've been working into this part of the diagram with the stapling and modifying peptides, but I will also perform virtual screening of compounds, chemical compounds, not only peptides. And I will perform several analyses to end up discovering molecules with non-peptidic scaffold that will probably interact also with the exfoliative toxins. And also we are working with facial plate experiments. Carolina just mentioned working with this experiments. She will explain more about this, but in essence what we are doing is that we know by expressing different peptides into the surface of the phage, onto the facial surface, we can know if they bind to the protein, which is fixed into here, and then by performing several steps of washing and using steps and amplifying the phages that bind tightly to the target, we can end up knowing some peptides that will tightly interact with our targets, which in this case are exfoliative toxins. And we hope to characterize the interaction of those peptides once they are sequenced right with the proteins through in silico tools, and also by performing crystallography experiments. And then those peptides will be modified to get more potent drug candidates. And these are the members of our group. Carolina, which is here, Dr. Arne, Professor Arne, which is the group leader, and other members of the group. And this guy here is Johannes Kirschmeier, which is my supervisor in Austria. I will travel to Austria in December to carry out some experiments, in silico experiments with him. So thank you.
Yeah. You mentioned in one of your examples that to apply this kind of solution for drug development, you have to consider different things, the allergenicity or immunogenicity of the peptide and stuff like that. Do you think you could end up with a solution regarding the exfoliant toxin? And what would be the way to apply this drug? Would it be clean?
Yeah, that's
something you eat?
Now we're thinking more like ointments, right? Something that you put in your skin. So we have to take care. Also, I mean, I mentioned permeability, but in this case, the target is extracellular, so we are not really concerned about the process of internalizing the peptide. I think that's something that is easier in our case because it's an extracellular target, right? But we have to deal with stability against proteolysis because you know that there are a lot of proteases in the skin. So you have a molecule that will be fastly degraded and then it doesn't work. So, I mean, what we have been working is, I mean, we know that this linker that it will fit perfectly into the active site of the protein, and we are seeking for ways to optimize this structure to turn it resistant to proteolysis, but at the same time trying to modify it in a way that it will increase the affinity for the toxins, right? And also we are exploring the allosteric sites. For example, we are really confident that this internal alpha helix, which is characteristic of the toxins, have an important role in the regulation because Molitor obviously is interacting with ectodomin 3. So by designing molecules that will bind to the internal alpha helix, we hope that we will impair the interaction of the toxins with ectodomin 3, which is a critical step prior to cleavage. Right.
Hello. Congratulations, nice talk. Do you use some comparison between the RMSD of the carbon alpha between the able form and all after the docking and dynamics with the
But molecules.
the last one you the two proteins.
Oh. This one?
Yes.
This one, okay. Well, I have simulated, for example, the protein here. Just ectodomin 3 and the protein is really stable, right? I think the most critical step is this one, because when you want to add an additional ectodomin, because you know it's like there are several ectodomins in protein. I mean, I don't really worry about what comes here because it is far away from the protein, it will not interact with it. This ectodomin is critical because, I mean, the protein has to somehow to bind to this region, right? And if you check the conformation that is modeled by alpha of this model in the alpha form, you see that the peptide will have this information, this one in here, the linker, right? But you see that the glutamate resin is really far away from the active site, so somehow it has to adopt this final conformation. So when you do that, this ectoderm will fit really close to the proteins, creating steric clashes. So to prevent that, you have to rotate this ectoderm. And we did that in sort of manual way. But then we perform very long empty simulations, and the system really stabilizes into this configuration, where you see the loop here, the linker, is really inserted into the outer conformation, which will be cleaved. You see the ectoderm 3 here interacting with this internal alpha helix, and the rest of the were determined to be important for recognition are here in this beta strand, and they're interacting closely with this region of the protein. And then you see ectoderm 4 adopting a conformation in which it really stays in a very specific conformation, because these calcinags are here stabilizing the interaction between both ectoderms. I didn't show it here, but here probably you can see. There are several acidic residues here in coordinating the calcinags in both domains, so they really stay together in this particular conformation because of this stabilization here.
Very good. And about the alpha that you have to
yeah, it's really, I mean, in terms of PLDBT, the metrics that they use for model validation is really good. I didn't show it, but you can check it in, because it is already available in Unicode, right? You can download that model, and it's really, because I mean, these proteins are all really similar. Before I use AlphaFold, there were homology models based on these structures, because there are crystal structures of closed organoids. So, I mean, the structure of this modeling is not really huge, I think.
Thank you.
Thank you.
Thank you very much, Dr. George, for your presentation. Next, I'd like to invite for the last talk before our lunchtime, a PhD candidate of microbiology, also from São Paulo State University, Caroline Gislene.
Olá, bom dia a todos. Primeiro eu gostaria de agradecer à comissão organizadora pelo convite, principalmente ao professor Vasco e à professora Flávia, e pedir desculpas, né, porque a minha palestra será em português. So sorry, I don't speak English very much, so is this, ok? Bom, hoje eu vou apresentar principalmente a proteína que eu estudo no meu projeto de doutorado. Essa proteína é a proteína esfoliativa C de Staphylococcus aureus. E no caso, ela é um pouco diferente das demais. Ela é um pouco diferente das demais toxinas esfoliativas, porque além de causar esfoliação da pele, ela também tem um potencial necrótico. Bom, primeiramente, nós temos que entender, né, o porquê que é importante estudar essas toxinas esfoliativas. Essa, em específico, ela é liberada e produzida pela bactéria Staphylococcus aureus, que é uma bactéria do gênero Staphylococcus, coco, gram-positivo e não imóvel. Além disso, ela apresenta uma alta capacidade de dispersão, resistência de secação e consegue sobreviver em ambientes não fisiológicos. De forma geral, esse micro-organismo ele é considerado um micro-organismo comensal. mas, além de ser considerado um micro-organismo comensal, ele também tem o potencial, né, de causar doenças em diferentes mamíferos. Dentre eles, os seres humanos, acho que parou. Som, dá para ouvir? Dentre eles, né, nós temos o ser humano, então ele foi responsável já por causar diferentes doenças, como endocardite, peritonite, choque séptico, infecção do trato urinário e doença inflamatória pélvica. Além disso, né, mais recentemente descoberto, essa bactéria ela foi responsável por causar algumas manifestações clínicas na pele de animais, principalmente em cães e, mais recentemente descoberto, né, a epidermite exudativa em suínos. Então, essa doença era comumente causada por Staphylococcus aureus. Mas em 2007 foi descoberta uma cepa de Staphylococcus aureus que causou, né, a epidermite exudativa em suínos em um rebanho de suínos. E o principal fator de virulência envolvido nessa manifestação clínica foi a toxina esfoliativa C, a EXHC. Bom, a EXHC, ela é, né, uma toxina esfoliativa pertencente ao grupo dessas toxinas, e ela é produzida, como as demais, por bactérias do gênero Staphylococcus. Portanto, ela é uma serinoproteinase glutamilopeptidase, apresentando como sítio catalítico serina, histidina e ácido aspartico, como o meu colega de trabalho já falou. E ela cliva, né, especificamente uma proteína da pele de mamíferos, que é a desmogleína 1. Então, a bactéria, ela libera essa toxina esfoliativa, a toxina, ela entra em contato com a epiderme e isso, né, garante ocorre a clivagem da desmogleína 1 e uma célula se separa da outra na epiderme. Esse processo, ele causa a esfoliação da pele de mamíferos e também cria uma porta de entrada para que o micro-organismo penetre e alcance outros tecidos do hospedeiro. É interessante que, como já foi dito anteriormente, né, existem diferentes toxinas esfoliativas. As mais estudadas são aquelas produzidas por Staphylococcus aureus, certo? Foram nomeadas de EPA, EPB, ETD e, mais recentemente, a ETE. Essas são predominantemente responsáveis por causar uma manifestação clínica muito conhecida em seres humanos, que é a síndrome da pele escaldada estafilocócica. Bom, mas, né, existem outras toxinas esfoliativas produzidas por outras espécies de estafilococcus, como estafilococcus icus, cromógenes, ciuri e seus intermédios. É interessante que cada toxina ela apresenta, né, uma especificidade à desmogleína de um hospedeiro. Por exemplo, as toxinas produzidas por Staphylococcus aureus, elas clivam preferencialmente a desmogleína 1 humana, enquanto as produzidas por Staphylococcus icus clivam preferencialmente a desmogleína 1 suína, causando a epidermite exudativa em suínos. Essa doença, ela causa grandes prejuízos à veterinária, uma vez que ela causa, né, a desidratação dos suínos recém-nascidos e pode levar à morte desses animais. Em 2007, né, foi descoberta uma cepa de Staphylococcus aureus, foi responsável por causar a morte de inúmeros suínos na China, e ela era EXHC positivo. O que isso significa? Que o principal fator de virulência envolvido nessa manifestação clínica foi a EXHC. Bom, nesse momento, essa proteína ela se tornou alvo de estudo de pesquisadores. Em 2011, perceberam que, além de causar a esfoliação da epiderme de suínos, ela também podia causar a esfoliação da epiderme de ratos, né, de murinos. Além disso, o que foi mais curioso é que essa toxina também causava necrose celular de diferentes linhagens celulares de mamíferos. Isso, até o momento, é uma exclusividade da XHC. Então, nenhuma das outras toxinas esfoliativas tem esse potencial. Bom, então esse foi o artigo científico, né, que publicou essa novidade da toxina esfoliativa C, e eles testaram diferentes linhagens celulares de fibroblastos murinos, também testaram macrófagos e linhagem tumoral de murinos, certo? Sendo que a linhagem modelo do artigo, né, que eles mais utilizaram para fazer os experimentos científicos, foi a linhagem DHK21, que inclusive eu também utilizei no meu projeto de pesquisa. Então, essa linhagem é uma linhagem de fibroblastos renais, de hamsters recém-nascidos, e a XHC ela tem potencial de causar necrose celular dessas linhagens. Como que foi o delineamento experimental dessa pesquisa, né? Então, primeiramente, eles expressaram, purificaram a XHC na sua forma selvagem, né? E aplicaram na linhagem DHK21. Ao perceberem que ela, né, completa, causava necrose celular dessas células, eles geraram diferentes fragmentos dessa proteína. Então, nós tivemos aqui quatro diferentes fragmentos dessa proteína sendo gerados, e eles testaram novamente na linhagem celular. Então, o primeiro fragmento, né, ia do resíduo de aminoácido 1 ao 78, posteriormente 1 a 128, né, e assim sucessivamente até gerar uma proteína completa. O que eles perceberam durante esses resultados? Eles perceberam que o único fragmento que não causava necrose celular era o primeiro fragmento, que ia do 1 ao 78. Sendo que os demais, eles causavam a necrose da linhagem celular na mesma proporção. É interessante ressaltar aqui que nós modelamos esses fragmentos, né, estruturalmente, e eles se modelam de acordo com a estrutura completa da proteína, certo? Então, assim, eles estavam estruturados e modelados quando eles realizaram os estudos. Bom, a partir disso, no artigo, eles determinaram que a região dos resíduos 79 a 128 era responsável dentro da XHC por causar necrose celular. Interessante que nessa região nós temos o quê? A histidina catalítica. Então, a histidina, né, que forma a tríade catalítica responsável pela esfoliação da pele de suínos e murinos, certo? Eles fizeram uma mutação pontual nessa histidina catalítica e observaram que a esfoliação da pele foi perdida por essa toxina, mas a necrose celular ela permaneceu. Então, eram mecanismos de ações independentes, certo? Bom, o mais surpreendente dessa toxina esfoliativa é que no mesmo ano eles também testaram essa proteína na presença de macrófagos murinos. Então, o experimento foi o seguinte: eles uniram em um nanoambiente macrófagos, uma cepa de Staphylococcus aureus e a XHC. E perceberam que a XHC inibia a fagocitose da Staphylococcus aureus pelos macrófagos. Então, os macrófagos não conseguiam fagocitar a bactéria na presença dessa proteína. Então, além de causar esfoliação da pele, necrose celular, a XHC ela também tem uma importante, né, função de inibir a resposta imune inata do hospedeiro. Então, ela inibiria esse processo, né, dos macrófagos fagocitarem as bactérias de Staphylococcus aureus. Por essa razão, nós podemos classificar a XHC como uma proteína moonlight, ou seja, uma proteína que apresenta múltiplas funções, pois ela causa esfoliação da epiderme de suínos e murinos, necrose múltipla de células e ainda consegue inibir a resposta imune inata do hospedeiro. Então, inibe que o hospedeiro consiga, né, fagocitar a bactéria que está liberando essa proteína. Dessa forma, é extremamente necessário, né, buscar sítios secundários da XHC que modulem essas diferentes funções. Porque para uma proteína executar diferentes funções, múltiplas funções, ela precisa ser ativada por esses sítios secundários. Então, o nosso objetivo sempre foi buscar quais eram as regiões da proteína que modulavam essas múltiplas funções. Bom, então aqui, né, eu escrevi o porquê, né, de nós estudarmos proteínas moonlight de micro-organismos patogênicos, pensando na XHC, né, que é uma proteína que já apresenta atividade esfoliativa. O fato dela apresentar potencial necrótico e potencial de inibir o sistema imune inato do hospedeiro é extremamente alarmante. Por quê? Porque a maioria do surgimento de novas doenças, epidemias, eles estão relacionados com a negligência, né, desses mecanismos de ação recém-descobertos. Por essa razão, pensando que o artigo científico anterior que eu mencionei para vocês havia determinado a região responsável pela necrose celular, o objetivo do nosso trabalho era identificar especificamente quais resíduos de aminoácidos estavam envolvidos nesse potencial necrótico. Porque a partir disso, né, nós conseguiríamos buscar inibidores específicos para esse mecanismo de ação. Bom, então, o que o meu grupo de pesquisa fez? Primeiramente, nós realizamos um alinhamento primário, né, da XHC com as demais toxinas esfoliativas já descritas em bancos de dados. Essa aqui, ó, é a região entre os resíduos de aminoácidos 79 ao 128, que foi determinado como fragmento responsável por induzir a necrose celular. Ao comparar com as demais toxinas esfoliativas, foi possível observar que existe um sítio conservado em todas as demais esfoliativas, exceto na XHC. Então, enquanto nas demais esfoliativas eu possuo, né, lisina, que é um resíduo positivo, na XHC eu apresentava glutamina, que é um resíduo neutro. Outro resíduo de aminoácido altamente conservado em todas as demais toxinas esfoliativas é a fenilalanina, né, nessa posição 84. Com exceção da XTB, de Staphylococcus pseudointermédios, que apresenta uma tirosina na mesma posição. Todavia, tanto fenilalanina como tirosina são resíduos de aminoácidos aromáticos, enquanto que na XHC nós possuímos, né, uma asparagina, que é um resíduo não aromático. Outras regiões que foram interessantes, né, que nos chamaram a atenção a partir desse alinhamento primário, é a arginina 82, o resíduo positivo, E a arginina 125, né? Também positivo, vamos para a arginina. Que nas demais toxinas esfoliativas eram substituídas por resíduos de aminoácidos neutros. Bom, apesar, né, desses resíduos estarem próximos na sequência primária e distantes da arginina 125, ao gerar o modelo estrutural do fragmento necrótico, foi possível observar que todos esses resíduos estavam próximos estruturalmente, né? E ao gerar o fragmento, ao gerar a proteína completa, né, o modelo estrutural da proteína completa, foi possível também observar que esse fragmento ele continuava nesse novelamento, que eu coloquei aqui, né? E ao traçar a área superficial da enzima, é possível perceber que esses 4 aminoácidos se encontram superficialmente na proteína, ou seja, não no cerne da proteína. Isso indica que elas podem estar envolvidas, esses 4 aminoácidos podem estar envolvidos no potencial necrótico da XHC. Bom, a partir dessa avaliação in silico, nós montamos, né, o nosso delineamento experimental, como seriam realizados os experimentos, para verificar se esses resíduos estavam realmente envolvidos na atividade necrótica da XHC. Então, primeiramente, nós expressamos e purificamos a proteína no seu estado nativo, ou seja, né, sem nenhuma mutação, e nós geramos 5 mutantes diferentes da XHC, sendo o primeiro dele com 4 mutações, né, nesses 4 resíduos em uma mesma proteína. Então, nós geramos aqui esse mutante trocando a arginina 82 por alanina, a asparagina 84 por fenilalanina, que era o resíduo de aminoácido conservado nas demais ETs, glutamina 86 trocamos por lisina e a arginina 125 por alanina. Esse aqui também era conservado nas demais toxinas esfoliativas. E após, né, fazer os testes com esse mutante e a proteína selvagem, nós depois geramos 4 novos mutantes com mutações pontuais para verificar realmente qual desses 4 aminoácidos estavam envolvidos na morte das células BHK21. Durante o processo de purificação, foi possível perceber que todas essas 4 proteínas recombinantes, elas eluíam, né, como dímeros em solução. Isso é uma informação que já estava presente na literatura. Então, em um dos artigos, né, que estudaram a XHC, eles classificaram essa proteína como dímero. E esse resultado foi bem interessante porque indica que essas mutações, elas não interferiram no estado liponérico da proteína. Provavelmente, esses resíduos não fazem parte da interface da nossa proteína, da interface, né, de oligomerização do dímero. Bom, então nós expressamos, purificamos em forma solúvel, na sua forma solúvel, e nós testamos o enovelamento, nós avaliamos, na verdade, o enovelamento dessas proteínas por dicroísmo circular. Então, a gente tinha que confirmar que essas proteínas recombinantes estavam enoveladas para seguir com os experimentos, né, em linhagem celular. E aí foi possível observar por dicroísmo circular, né, que todas as 5 proteínas recombinantes estavam enoveladas e com alta similaridade em porcentagem de enovelamento. A partir desses resultados, nós seguimos com os experimentos em linhagem BHK21. Então, primeiramente, foi cultivada a linhagem BHK21. Nós plaqueamos 1 × 10⁴ células por pulso. E no dia seguinte, nós drogamos essas células, né, com as proteínas. na sua forma selvagem e mutante. Quando observado aqui pelo gráfico, foi possível concluir que realmente a XHC ela tem o potencial de causar morte dessas células. Então, ó, em concentrações de 15, 30 e 60 micromolar, a XHC ela diminuiu a viabilidade celular em 40, 60 e 70%, respectivamente. Então, a XHC causa realmente a morte da linhagem DRK21. Diferente do observado para a XHC com as 4 mutações pontuais. Então, as 4 mutações pontuais, elas inibiram, né, a capacidade da proteína de causar necrose nessas células. Esses resultados, eles indicaram que, provavelmente, né, os 4 resíduos de aminoácidos que nós selecionamos, eles estavam envolvidos na atividade necrótica da XHC. A partir desses resultados, nós fomos, né, para os experimentos de mutação pontual. Então, nós testamos a XHC com mutação pontual arginina 82 por alanina e a XHC com mutação pontual asparagina 84 por fenilalanina. Ambas as proteínas mutantes, elas não causaram, né, diminuição significativa na viabilidade celular da BHK21, ou seja, a ARG82, o aminoácido ARG82 e a asparagina 84, eles estavam envolvidos diretamente na necrose celular e eles eram essenciais para que a proteína conseguisse causar a morte dessas células. Já no caso das proteínas com mutações pontuais, XHC glutamina 86 por lisina e XHC arginina 125 por alanina, em alguns casos, em elevadas concentrações dessas proteínas, foi possível observar que houve, né, uma diminuição significativa da viabilidade celular da DHK21. Então, ó, por exemplo, né, ao se adicionar 60 micromolar dessas 2 proteínas recombinantes, houve uma diminuição da viabilidade celular de 34 a 22% de morte dessas células. Mesmo assim, essa morte ela não é tão significativa quando observado, né, a morte causada pela mesma concentração da proteína selvagem, que causou uma morte de 70% das nossas células DHK21. Esses resultados, eles sugerem, né, que esses resíduos de aminoácidos, eles não são cruciais para causar morte celular das células de mamífero, mas que eles interferem no potencial necrótico. Bom, além desses resultados in vitro, o meu grupo de pesquisa ele trabalha com a área de biologia estrutural. Então, nós geramos, né, estruturas de proteínas através da cristalografia de proteínas. Então, em um primeiro momento, nós tentamos, né, cristalizar todas as proteínas recombinantes e a que teve resultados mais satisfatórios foi a proteína com 4 mutações pontuais. Então, nós obtivemos cristais dessa proteína e a partir desses cristais, nós resolvemos a primeira estrutura tridimensional de uma toxina esfoliativa que tem potencial de privar a desnucleína suína. Todas as demais depositadas no proteína da Bact são, né, toxinas esfoliativas que clivam preferencialmente a desnucleína humana. Além disso, a resolução que nós conseguimos com essa estrutura cristalográfica foi impressionante. Então, nós conseguimos uma resolução de 1,57 anos, que é uma resolução excelente para que a gente consiga, né, avaliar de perto, né, os mecanismos de ação necrótica, termolítico e até mesmo o como que a proteína pode estar atuando para inibir a resposta imune inata do hospedeiro. Bom, então aqui está a estrutura, né, tridimensional da XHC mutante. E a partir dessa estrutura, nós fizemos um alinhamento estrutural com as demais toxinas esfoliativas já depositadas no proteína Bact. Foi possível observar que, em questão de alinhamento estrutural e também de alinhamento primário, a XHC ela é mais similar, homóloga, né, a ETA Staphylococcus aureus, que é a toxina esfoliativa mais estudada dentre todas que nós descrevemos aqui. Então, ela é a mais próxima da XHC. Bom, a partir desses resultados, durante o meu projeto, eu expressei e purifiquei tanto a ETA, que é a mais similar à XHC, quanto a ETE, que de Staphylococcus aureus, e testei em linhagem PHK21. Eu gostaria de observar se essas proteínas também possuíam um potencial necrótico nessa linhagem. E aí nós não tivemos resultados positivos. Isso é um indício de que provavelmente, né, a XHC ela é uma das únicas toxinas esfoliativas com o potencial de causar morte de células de mamífero. Através da estrutura tridimensional da XHC mutante, nós geramos um modelo da estrutura tridimensional da XHC selvagem. Então, nós temos mutações pontuais naqueles 4 resíduos de aminoácidos já mencionados. E nós pegamos, né, utilizamos essa estrutura no software CAT+. Nesse software, foi possível identificar as cavidades dessa proteína, sendo que foram identificadas 9 cavidades superficiais. É interessante que 2 dessas cavidades são de interesse para nós. Uma delas contém o sítio ativo responsável pela atividade esfoliativa, certo? E a outra tinha os 4 resíduos de aminoácidos de estudo do meu projeto de pesquisa, que nós descobrimos que estavam envolvidos no potencial necrótico da enzima. Então, todos os 4 resíduos estavam aqui. A partir desses resultados, nos surgiu a dúvida se essas mutações que causam, né, inibição da atividade necrótica poderiam influenciar na atividade enzimática da XHC. Por essa razão, nós testamos a proteína mutante utilizando um substrato sintético, que o meu colega já mencionou anteriormente, para avaliar se a atividade catalítica da enzima iria mudar significativamente. Tanto a proteína selvagem quanto a proteína mutante, elas apresentaram uma eficiência catalítica muito similar. E isso é um indício, né, de que provavelmente essas mutações não interferem na atividade catalítica da enzima. E provavelmente, né, não vão causar uma interferência na esfoliação epidérmica causada pela XHC em suínos e murinos. Bom, a respeito das perspectivas, né, desse trabalho. Então, como nós conseguimos desvendar os resíduos de aminoácidos envolvidos no potencial necrótico, obviamente, um dos objetivos do trabalho é buscar inibidores específicos para esses 4 resíduos de aminoácidos. Mas nós utilizaremos, né, a técnica do phase display nesse caso, que é uma técnica na qual você imobiliza o seu alvo e utiliza de uma biblioteca de fagos contendo peptídeos no capsídeo para interagir com a sua proteína. Então, uma biblioteca de 10 elevado a 10 peptídeos. A partir de lavagens, né, você vai conseguir deixar acoplada a sua proteína apenas os fagos que apresentam alta afinidade com a proteína. Posteriormente, nós eluímos esses fagos de alta afinidade, amplificamos e sequenciamos para observar quais peptídeos, né, tiveram alta afinidade de interação com a proteína. Mas por que utilizar essa técnica, né, e não utilizar uma técnica computacional, por exemplo, que vai focar no meu domínio necrótico? Porque, além de buscar inibidores, essa técnica ela pode nos dar indícios, né, de potenciais sítios secundários da enzima por vias computacionais. Então, depois eu posso observar esses peptídeos no computador e avaliar em que regiões esses peptídeos estão se ligando na minha proteína. Os sítios alostéricos e os exossítios são alvos do nosso grupo de pesquisa no momento, porque eles que modulam, né, essas proteínas com propriedades modulares. Além disso, a partir das sequências peptídicas, eu posso, inclusive, detectar um peptídeo que contenha, né, uma região similar à da desnucleína onda, da SG1. Isso pode me dar um indício, né, da região de reconhecimento das toxinas exfoliativas com o seu substrato específico. E também é algo do meu estudo buscar com quem a XHC está interagindo na linhagem DH21. Porque até o momento nós sabemos que ela causa necrose celular, mas nós não sabemos com que biomolécula dentro da DH21 ela está interagindo para desencadear esse processo de morte celular. Bom, eu queria agradecer aos meus colaboradores, né? Sem eles esse trabalho não seria possível, principalmente meu orientador, o professor Arne, os meus colegas de trabalho, Marília, Jorge, Ricardo Mariucci, a Ângela, o Fábio e a Alana. E aos órgãos de fomento. Muito obrigada, pessoal.
Very much, Carolina. So now we are going to have a break for the lunch. So if you feel like extending the discussion with the professors and the researchers, they are going to have lunch in Academia da Carne in José Dias de Caio Avenue. So you are welcome to join them to have lunch together. And that's for lunch. And for dinner, they are planning to go to the famous restaurant of Minas Gerais called Chapuri. So they have a table reserved for 7:30 p.m. Thank you. We will be back at 2 p.m. Okay?